Okay, ji, welcome you to today's lecture. Today we focus on Laplace transform, and there are things that need to be discussed. So, what is Laplace transform? So, um, actually, this is a mathematical transformation from we call it time domain to frequency domain. So, the formula is f of s is equal to, you have to do an integration that is 0 negative to infinity, and f of t exponential minus st. So what is the advantages? So basically, if we look at the advantages, so first one is that it converts ordinary differential equation to algebraic equation. That makes our life easier to solve. And next thing, it is used to simplify the convolution integral. So these are the basic benefits that we achieve when we do this type of mathematical transformation. So actually frequency domain is nothing, this is actually a mathematical transformation. Okay, so there's because we do the mathematical transformation, so that's why to convert back we also have to do inverse Laplace transformation. So because if we do something to transform in some other domain, we have to convert it back. For that we have a formula which is also based on integration, but this formula is a bit complex. Okay, so when you apply this, you can easily calculate the inverse transformation. Now to overcome this, there's a Laplace table developed to use it for simplify to calculate the inverse Laplace transform. So there are a few theorems that we need to discuss today, and first theorem was theorem 1. Theorem 1 is for multiplication. So it's very simple that if you take the Laplace and scalar multiply the time, so it is equal to k times f of s. So theorem 2 is for sum and difference. Again, if you take the Laplace, because it follows the linearity, is followed by the Laplace, so that's why this is equal to plus minus Laplace of f2. So similarly, this is the theorem number 3 is based on differentiation. So for differentiation, if you take the Laplace of the derivative of f of t, this is actually equal to s f of s minus limit when t tends to 0 f of t, that normally written as s f of s minus f of 0. So it's with the initial conditions. So you can extend it up to nth derivative. So for nth derivative, what you have to do as per ns minus then limit t tends to 0, and then you have Sn minus 1 f of t plus Sn minus 2 derivative of f of t plus so on plus and minus 1 derivative of f of t, or we can write it at Sn f of s minus Sn minus 1 f of 0, then minus Sn minus 2 f dot of 0 minus so on minus f n minus 1 derivative 0. So this is the generalized formulation for differentiation. Now if I move to next one, this is theorem number 4 that deals with integration. So integration is how we solve the integration. Theorem number 4 for integration says that these are very basic theorems, but what we are interested will become next two theorems. For integration, if you know that if you have something like that, you just have to put f of s divided by s, okay, in integration. Now assume that you have more than, for example, if you have more integrals and they are start from 0, tn minus 1, tn minus 2 up to so on. For example, you have nth integral, okay, so you have f of t, spread f of t, and you say that you have t tau dt1 up to dt n minus 1. So in that case, if you apply the Laplace, it's simply equal to f of s divided by s power n. So this is the theorem that deals, these are basic theorems, okay. So important theorem that we are looking is theorem 5, that is deal with the shift in time. Shift in time, this is very important theorem. So for shift in time, for example, if you take the Laplace and your system is t minus capital T, us of t minus capital T, so in that case it's simply equal to exponential shift in frequency domain or Laplace domain, okay. So this is what we have now. This is important theorem, but the most we commonly used is initial, these two theorem, initial value theorem So for initial value theorem, we say that when limit t tends to 0, f of t, okay, this is the initial value, is equal to, in Laplace when s tends to infinity, so initial value in time is equal to final value, that is infinity, value at infinity, s time s of s. So this is very important, and this is used us to calculate the initial values in the system. And there's loss theorem, and this is also very important and used a lot, is final value theorem. Now final value theorem means that in control system we normally very much interested in the final value of the response. So this theorem used a lot there, and it says that limit when t tends to infinity. So in initial theorem you have t tend to 0, but here when t tends to infinity, f of t is equal to limit when s tend to 0, s f of s. So this is very important theorem where we can use it to find the final value of the system. Okay, now one thing is very important. This is only possible if and only if your f of t is stable. So we will discuss why we say this, because if this is unstable, so final value go to the infinity, so there's no point of calculating the final value. Now we will look some examples on these. For example, you have f of s given to you, that 5 divided by s into s square plus s plus 2. Alright, now and if I ask you to find the final value, so you have to use limit t tends to infinity, f of t is equal to s tend to 0 as f of s. So from here I just plug in the values, so it becomes limit when s tend to 0 s times 5 divided by s into s square plus s plus 2. So s will be cancelled out when I put the limit s into 0, it becomes 5 by 2. So this is the final value when t tends to infinity. So this helps us to find us the final value of the system. So this is very important theorem we will use for system analysis that we will look after this video. So there's one theorem that is known as theorem number 8, and it is about complex shift. So what is complex shift? When you have to take the Laplace and you have exponential, for example minus plus exponential power 80 f of t is multiplied, what you have to do is equal to, look here, it's very important, this sign is minus is above and plus is below. Here sign is changed, it becomes plus minus alpha. So this is a frequency shift in the frequency domain. Okay, so these are very important concepts that we can use for Laplace transform. And last theorem too is also need to be for completion is real convolution. As you know that convolution integral is something that is complex manipulation. So in frequency domain, multiplication is equal to Laplace of convolution of f1 convolves with f2 of t. So this is another benefit that we get when we use the Laplace transform. So this is what we have in theorems. Now the another thing in Laplace, we have to take the inverse Laplace transform. So because when you do the transformation, you have to go back to Laplace transform. When we do the inverse Laplace transform, we normally use tables, but in tables all the transformation are not available, so we have to use the partial fraction. So partial fraction we have to use to solve our problems and make it compatible to the what you say table. So in that case, so in first one, which has a simple poles, so we normally call roots as the poles, simple poles. So in that case, if you have g of s, that is equal to q of s divided by p of s, or in other words q of s divided by, you have simple poles like distinct poles, okay, s1, s2, so on up to s plus sn. So in that case, you can write g of s as k1 divided by s plus s1 plus k2 s plus s2 plus so on plus kn s plus sn. So this is the way you easily. Now the thing is to find the k values. There are different ways, cover up method, comparing coefficients that you can use to find the values of k. So let's do cover up method quickly, how we apply this. So in cover up method, for example, you are looking for k1, so it's very easy. It's equal to, you just have to multiply the pole with g of s and put s equal to minus s1 in that case, because you have to put this equal to 0. So this is cover up method where you can easily calculate the values. Okay, now the next one is repeating roots or has multiple order pole. So in that case, what you have g of s that is equal to q of s, where p of s same thing, but here the thing is a bit different, because we have repeating roots here. So how we do that? Now for repeating roots, the idea is for example, we have I wrote a very simple example for understanding. Okay, so for example, we have s plus s1 and we have s plus s2 power 2. So this is a repeating case. So in that case, how you wrote it in partial fraction, you wrote it similarly. You say that, okay, you have k1 as s plus 1. This is the same way you calculated the previous case, but for repeating you have to do or separate, represented by a separate what you say coefficient, so that you understand. So I take s plus 1 and then s2 whole square. So how you calculate the so for k1 is the same method. Cover up method says s1 g of s and put s equal to minus 1. What about a1 and a2? Now for the highest value of a, that is a2, first solve that and put cover up method technique, that is s plus s2 power r g of s. So and put s is equal to, of course, the root, that is minus s2. Now for a1 you have to take the derivative of this one, so you have to continue until you find all the roots. Why you take the derivative? So it's very simple to understand, because look here, a1 is with 1 power, so you have to take the derivative so that its power is 1. So that's why we have to take the derivative. From this you can calculate the results. If I move to the next one, and it's the last one, complex roots. So so the third one, complex conjugate pairs. Now in complex conjugate pairs, normally how we do that? We do the same thing. So in complex, you know that you have s equal to minus plus j omega, this is s1, and s2 is equal to minus real part minus j omega. So for that case you have to calculate similarly. So for s1 you just put cover up method, that s plus sigma minus j omega times your g of s and put s equal to minus sigma plus j omega. Similarly for second one you have to put s plus sigma and plus j omega times g of s. So this is similar because these are distant in nature, so you don't need to do anything extra. So this is the way you can do Laplace. I just overview the Laplace because we will go to look at the responses, so we need to understand this before we are going to the discussion on the response of the system. So thank you. So I will stop here.